guys, very good morning to every one of you. Guys, today we are going to see about the next chapter in the fluid mechanics, especially this is episode number 2. So if you haven't watched the first episode, you please do go and watch the first episode. And in the first thing, I just covered about the cavitation number and how the problems will be related to the submarine, the blades and all, how it will get affected. And a little bit of extra things about the fluid mechanics I just conveyed in that video in a detailed way. So in the second video, I'm just going to cover about the Newton's law of viscosity. Because in this Newton's law of viscosity is A equal to B means there should be a relationship between A is equal to B. So why this Newton's law of viscosity is most important in the fluid mechanics? So let me explain to you in a simple format so you can have a good understanding about it. Just one sec. So let us suppose there is a plate over here and here lot of fluid is going. It's a water fluid going. But at the beginning you can see here the velocity will be 0 and as it's going in hyperway, here velocity will be 10. So you could have see here the distance comes. So let us name it as y. And later on see as the velocity it means per a certain amount of distance it goes on in an increasing way. So it also tells about the shear force. It means there is an acting of friction between the two layers. See, as here it's 0 and 1, 2, 3, 4 like that. Because the speeds gets up so much increase. So at the bottom you just see all the molecules here are fixed. So it is fixed with the it means flat molecules. And the top molecules will also move. So this bottom molecule will tends to resist. We don't go like that. It will resist. It's A, it's B means this B molecule will resist A. So at the top of it there will be other molecule just C. So this A molecule will resist C molecule. So this is 0 meter per second means here 1 meter per second, 2 meter per second. So this velocity movement tells about the shear force. It means the resistance within the internal of the liquid. So you can see here the velocity is there and here the distance is there. So that means we need a relationship between velocity and the distance with respect to the shear force. It means shear force is also other type of friction. So tau equal to, it means tau directly proportional to velocity is also there. This distance is there. So du by dy. So at upper portion tells about the velocity and bottom portion tells about the distance. So it means that say there's a indirect relationship between, because you just take water and you just pour it to the surface, it moves easily. But same you just take oil and you just pour into the bottom surface, it means the ground, it won't flow easily because both of them has certain amount of density and as well as viscosity. Because this viscosity only resists this kind of velocity movement and along with the distance. Whenever you just see guys, as I told before, because viscosity is so simple guys, viscosity is internal resistance of two fluids. It means internal resistance of two layers. So you could have see here 0 meter per second, here 1 meter per second. So this is one layer and this is another layer. So A, B, this layer moves like and this also moves, but the internal layer also resists the A layer to opposite direction. So that's why viscosity is called as internal resistance of the two layer in respect to the each of the every medium. So oil has different viscosity, water has different viscosity, mercury has different viscosity. So this tau directly proportional to du by dy. Now to make it equal we need to put a constant. So tau equal to nu du by dy. So this nu is a constant thing. So for oil it's the same, for water it comes under the certain amount. So this is the Newton's law of viscosity. So I think so you can understand now. Tau directly proportional to du by dy and tau equal to nu du by dy. So this nu is a constant, this is called the viscosity. So that's why it's been represented here. So I think so you can have a basic understanding. So you can see here the shear stress tau on the fluid element is directly proportional to rate. See guys, it's rate. See, since it's a dt is given, it means dt is also represented as the distance. So rate of shear strain is the most important thing that you have to just note it down. And see, the next thing is the viscosity may be defined as shear stress required to produce unit rate of shear strain. So it's been so simple. So you just this mu is a viscosity equal to you just tau dy by upon du. So you just convert nu equal to tau divided by dy, which is d means, so just a second, nu dy, okay, dy upon du. I think so I just noted it in a wrong way. Let us again do again. Nu d, sorry nu du upon dy. So make it as a nu tau dy divided by du equal to nu. So you just make nu equal to tau upon du upon dy. So I think so now you just got. So the viscosity represents the viscosity is equal to proportional to shear stress and with the unit rate of shear strain. So this is a unit rate of shear strain. I think so you got a understanding. So this is entirely is called shear strain. Shear strain. So at the basic thing I will just explain what is shear stress and shear strain. So shear stress means this is a shear stress. So here they are fixed. Here in the upper portion you are just applying force. This is called a shear stress. So after a certain amount of time this tends to move. So you can see here this certain amount of angle is being moved. So this is called as rate of shear strain. For applying of force, how much the rate of shear strain is for, it means it's moved. So it means for example for oil you just take means. So how you can find nu equal to, it means shear stress, the shear stress we applied here by du upon dy. So based upon this you can find the oil's viscosity. I think so you can understand my point. Suppose if we do not apply any kind of shear stress, it means force we not apply and the velocity is not moving and the distance is not there, means everything will come into zero. So the oil is so much in a still condition, so it doesn't move in any format way. So that's why this zero might come. I think so you can have a basic understanding. So now we can just relate this. So you can see here. So this is the actual case scenario. This is upper layer, this is bottom layer. This lower layer will oppose the upper layer. See, this u is 5 means you see plus du means 5 plus 0.5. So again 5 plus 1, 5 plus 1.5, like that it will go on increasing. So let us come to the round of the question. Newton's law of viscosity relates to the velocity gradient and rate of shear strain. Yes. And the next thing is rate of shear deformation. No, shear deformation, it's not deforming. And shear deformation, yes, no, it is not. Everything is related to the rate. Here rate of shear strain and shear stress. Here you see guys, here Newton's law of viscosity. So the answer 1 is the right thing. So the next thing you can do, for a Newtonian fluid, shear stress is directly proportional to shear strain. No, rate of shear strain is okay. So rate of shear stress is no. Shear stress is directly proportional to rate of shear strain. This C option is the right one. So rate must be needed. So next thing, Newton's law of viscosity depends upon stress and strain in the fluid, shear stress. So what do you think the thing will come? So you can see a shear stress and the rate of shear strain. See, rate is that. So that's why the C is the correct one. Okay, in this thing, in Newton's law of it means in the Newton fluid, laminar layer flows between two parallel plates. It means two parallel plates is there, and here the fluid is flowing, and ratio between the shear stress and rate of shear strain. So it's so simple. Nu equal to nu du upon dy. So what they are asking, the ratio of shear stress and shear strain. So tau equal to dy upon du equal to nu. So tau divided by du upon dy equal to nu. So they are asking this. So what is the answer? B is the option. Okay. I think so I got my point. So we can just proceed forward. And I just told about the viscosity. Viscosity is a property of fluid by virtue which offers resistance of, it means resistance of one layer to the another layer, resistance to the movement of one layer over the adjacent of the another layer. It is observed between when two fluids have relative motion. So you just suppose for example you just take a water and you just made to pour in the surface area. So each and every layer will move in an opposite way. So at that time you can just understand what I am just telling to convey to you. So let me give you a small example so you can have a better and clear understanding. So I think so by looking upon this you can have a basic understanding. So let me show you one thing. So which one is okay, this thing. Okay, just consider this one. So you can see there's a lot of layers between them. So each and everything will be velocity will be here velocity 0. Here the velocity will be topmost velocity. Here the shear force applied. This is the area of the plate. So like that we should just consider. So internal resistance between this layer and the next layer. So this layer and this layer will have an internal resistance, that's called as viscosity. So I think so now you just got a basic understanding. So now you just see guys, viscosity is independent of the rate of deformation for the Newtonian fluid. See, for Newtonian fluid and non-Newtonian fluid both are different case scenario. See, for example, this nu equal to tau it means du upon d theta. So du upon d theta, it means du upon dy may be written as d theta upon dt. So it's both are the same things. Okay. So you can write here it means nu tau d theta upon dt. So like this also you can write. It means like this also you can write. So if tau is increased, if tau is, it means shear stress increase, then this viscosity will also increase. And if d theta by dt, it means rate of deformation. It means rate of deformation is increased, means you just see this nu will decrease. I think so you can have a basic understanding. So that's why you can see here viscosity is independent of rate of deformation for Newtonian fluid. Okay, and it's generally the viscosity of the fluid depends on both the temperature and the pressure, but depends on pressure it's rather weak. So this see guys, this viscosity depends on extremely on temperature, and pressure is very much less dependent. So you just see when you heat oil, the viscosity how it will happen, the viscosity start to decrease. But in case of, it means this is for only liquid case scenario. When you just take for a gas, when you heat, it means the viscosity tends to increase. It is for the gas. So as the video proceeds, I will just explain each and everything. So you can see here the next thing is given, causes of viscosity. Okay, why the viscosity is occurring? Because here you can see get the bottom layer, and here bubble, and here also bubble. So it means I am just saying this is layer. Here it's not color. So why this kind of thing are occurring? Because this both of the thing are water. So water and water, it means water molecules attract each other because of the cohesive force. See guys, there is two type of thing. One is cohesive, another one is adhesive. So cohesive means attracts each other. It means attracts other molecules. It means same molecular formula. Suppose water molecule gets attracted by the water molecule. For example, you just take mercury, and you just drop it means one drop here and the other drop here, and when you make it near, so mercury and mercury gets attracted easily. But for adhesive, different structures. For example, you just take Fevikwik. For example, I'm just saying Fevikwik, and alongside with the paper, plus and I'm pasting the paper. So for pasting paper, we use different molecular formulas like Fevikwik and paper. So that's why this is called adhesive. Adhesive means different of two other molecule layer we are just tend to attract, and cohesive means same molecule tend to attract. So here the viscosity happens mainly due to cohesive force, because cohesive means attraction of the both of the two molecules. And the second thing is in gases. See, this for liquid it will become for the cohesive, but in gases viscosity occurs mainly due to the molecular collision. So you just see guys, you just think this is a gas, and gas it won't be remain in a stable, it means stable condition as it's been present here. So the gas molecule will tend to move each and every direction so much faster. So this collision, lot of collision occurs. So viscosity of the gases comes from the collision. So you just make it remember. So we can just go to the next thing. Okay, how this temperature is related to the, especially for the viscosity. And if for some case scenario, if we heat, the temperature of the viscosity may increase or decrease. So how is this related? You just see guys, for viscosity of liquid, when we heat, it means when the temperature increases, the viscosity tends to decrease. But for gases, when we heat, the viscosity tends to increase. For liquid it tends to decrease, for gases it tends to increase. So based upon here, you can see here, see this viscosity is this much and this gas is this much. So for viscosity of liquid is so much higher. So for nu is about 1000 means, for gases it was 5. So you just see the difference between the viscosity of the liquids and viscosity of the gases. So that's why this kind of graph is given. So always viscosity of a liquid is so much higher when we compare to the gases. So you can see here the viscosity of a liquid decreases and the viscosity of the gas increases with increase in temperature. See, the temperature is increasing, the viscosity of liquid decreases, and the gas tend to increase. So that's why it's called as, so viscosity of the gas occurs mainly due to the molecular collision, but viscosity of the liquid occurs due to the cohesive force of the same molecules that's been present there. I think so you got a basic point of view. So now we then just go to the next one, so you can have a clear understanding. So first let us see some of the questions, so you gotta get a clarity. The viscosity of the liquid decreases with increase in temperature. Yes, that's of course. And while the viscosity of the gases increases with increase in temperature, that's also of course. The viscous force in the fluid occurs due to the cohesive force and molecular momentum transfer. Yes, definitely it's a truth. So for liquid, both the cohesive force and molecular transformation is occurs. But for gases, only molecular transformation, it means molecular transfer only is occurring. So it how to say means liquids cohesive plus molecular moment transfer. For gases, the cohesive is so less, 0.00001. But for molecular momentum transfer, this is about 99.9999%. So for gases, the molecular momentum transfer is so much high, but for liquid, the cohesive force is so much 99.999%. This is so much lesser. But when we compare with the real case scenario, for liquid also, it means Guys, you just see here what is there is given. It's given as a fluid, not liquid. They haven't just mentioned here liquid or gas. Suppose for the same thing, the viscous forces in liquid are due to the cohesive force and molecular movement transfer, means for liquid this molecular movement transfer won't come. Here they just ask for the combination of the fluid liquid alongside with the gas. So that's why this option is correct. I think so. You can have a basic this statement 2 validates for the statement 1. So the next thing you can go. In general, viscosity of a liquid increases with increase, and in gas it decreases with rise. That's of course correct. Viscosity is caused by the intermolecular force between intermolecular force. It means intermolecular force of cohesion and due to transfer of molecular momentum between the fluid layer, which in a form the liquid is former and the gas is later, contributing major part towards the viscosity. Guys, see this thing is a little bit correct, but of course it's not correct. You just come to a basic understanding. See, this R1 is a correct thing, because you can see guys, viscosity is caused by intermolecular viscosity. One thing, viscosity is coming from the layer. It means due to the layer, because this one layer of the molecule will also attract or repel the other molecule that's been present in the above condition. So that's why you can see viscosity is caused by intermolecular force of cohesion. Yes, definitely is correct. For liquid it comes, for gases the molecular momentum it comes, but here they is given fluid, so that's a mostly correct one. Yeah, and also results of which in liquid the form, it means the top portion of the intermolecular cohesion comes from the liquid, and for gases the later contributes measure. Yes, this is correct thing. But you just see viscosity in liquid increases while increase in temperature. Oh, this is a particularly wrong thing. So option D is the correct thing. So next thing we have to just look upon the basic formula. So formula is the most important thing that we have to just look upon, because for solving each and every problem, formula is so much important. So for viscosity, so nu equal to tau du upon dy. So shear stress, what it will mean? Shear stress means force, Newton, meter per second square. So equal to Newton second square per meter. So I think so. You got me. Yeah, sorry. Literally so much sorry. So here meter per second, and here meter will come. So we'll just going Newton second meter square. So okay, I think so. You got my point. Suppose if you put in a CGS unit, it means what will come? Dyne per second per centimeter square, or poise. So 1 poise equal to 1 dyne second per centimeter square. So if you change the centimeter square into meter square, it will change. So it means 1 meter equal to 100 centimeters. So 1 meter equal to 1000 millimeter. Suppose 1 millimeter equal to 10 power minus 3 meter. 1 centimeter equal to 10 power minus 2 meter. So I think so you can have a just a basic go through. So the other thing is, it is said in the MKS unit. So MKS unit you can see, for MKS unit it's kg force dot second per meter square. So CGS only it's been written in a centimeter. For MKS unit kg force dot second meter square. So CGS unit means what will come? You just think dyne second meter square, centimeter square. MKS unit kg dot force dot second per meter square. I think so you got my point, because Newton is generally represented as a kg per force. See, suppose for example force equal to pressure divided by area, or weight equal to mass per mass into gravity. So for weight it's about Newton, so that's why for Newton we are just giving kg. This is extra force is internally applied over that. So I think so you got my point. Next thing is, you can see what is the unit dynamic viscosity of the fluid poise equivalent to. Poise means what? Which one will come? Option C, dyne dot second per centimeter square. I think so you got my basic understanding. So we can just go to the kinematic viscosity. The next thing is very much important. Kinematic viscosity. In most of the question, viscosity will not be given, kinematic viscosity will be given. So why this kinematic viscosity is so much important? Because it tells the heaviness of the fluid. Because viscosity nu is just tells about the cohesion and intermolecular representation. It means how the layers of the fluid will work, layer by layer, how it will work. But kinematic viscosity equal to dynamic viscosity divided by density. So dynamic viscosity is this viscosity, dynamic viscosity divided by density. You just see guys, suppose how to say, for example let us for example I am just saying dynamic viscosity of it means for what I am just saying, for example this nu is 1000 and for density is also 1000, means it's about with the kinematic viscosity is 1. For mercury I am telling, for mercury the dynamic viscosity is so much lesser, they about 900 something, and it's about 3600. So you just compare this, it will come less than 1. So sorry, less than 1 it will come. So that's why the kinematic viscosity for the mercury will be so much, so it can slip through, it can flow easily. But for kinematic viscosity of oil, you just see about 700. The dynamic viscosity is so much higher, but the density will be so much less, 700 or something. But here it will be more than 1000. So the oil can't flow easily, and it also tells the heaviness of the fluid. So that's why kinematic viscosity is also so much important. So kinematic viscosity equal to dynamic viscosity divided by density, nu divided by rho. The SI unit of kinematic viscosity is, as nu is given, you just put a quick calculation, nu divided by density. So what is the unit of viscosity? Think quick. So Newton dot second per meter square divided by density, meter square plus meter, it means meter kg per meter cube. So equal to Newton second meter square into meter cube per kg. So this so Newton second into meter per kg. So how we can represent this kg in the Newton? So weight equal to mass into gravity. So you just make a calculation. So kg into meter per second square. So Newton. So you just go and replace it. So kg dot meter per second square into second into meter divided by kg. So kg cancel. So this. So meter square plus second. So viscosity equal to meter square plus second. So quick. So put the calculation so much quicker, so you can have a basic understanding. So CGS unit means what will come? For CGS means always convert meter to centimeter. So CGS unit of kinematic viscosity is centimeter square plus divided by second. Okay. MKS unit means meter square plus second will be there. So I think so you got my understanding. So the next thing is this, it means 1 centimeter square per second equal to how much? 1 stroke. So you just convert this into meter, means how much it will come. 1 centimeter to meter, you just convert. So 10 power minus 2 centimeter equal to 1 meter. So you just apply it, 10 power minus 4 meter square divided by second equal to 1 stroke. This is in time of meter, though this is in term of centimeter. So that's why it's the most important thing. So the next thing we can just go on. So you can see, for it means for viscosity and for kinematic viscosity, mostly a lot of difference won't be, little bit of same difference. In dynamic viscosity, in this viscosity, density won't be there, but in kinematic viscosity, density will be there. So nu equal to same, it means tau du upon dy. So this kinematic viscosity is nu upon rho. So I think so you got a basic understanding. Here the density will be represented here, kinematic. So here dynamic. So here dynamic density won't be there, here kinematic density will be there. So this kind of things you can just move on. So kinematic viscosity also refers to movement diffusivity in a fluid. So it means movement or movement diffusivity means it tells about indirectly about the how the transportation of the movement of fluid is been occurring with the density. So you can see here kinematic viscosity of a liquid decreases with increase in temperature, and for the kinematic viscosity of the gases increases with increase in temperature. So for dynamic and kinematic viscosity both are same. For increase in temperature you just consider for liquid gas temperature rises. So dynamic viscosity for liquid it decreases, for gas it increases. Kinematic viscosity for liquid same, decreases, for gases it tends to increase. I think so you got my point. So we can just proceed to the next one. So next one here it's been given for the same thing. For liquids both dynamic and kinematic viscosity or practically independent. Yes, for all the thing guys, for in case of liquid we should not consider the pressure. For liquid also, for liquid alone you just think, for liquid don't consider pressure don't consider. For gas we should consider the pressure. See, for mostly, but small, we neglect any small variation in pressure, small variation for dynamic viscosity, but for not for kinematic viscosity, since density of a gas is proportional to the pressure. Why you mention equal to say PV equal to m RT. So you know about this formula that's been coming in the fluid mechanics, thermal. So pressure equal to density upon rho T. So for that's why for gases we don't neglect this kind of pressure, but for liquid we usually tend to neglect this kind of pressure. I think so you got my point. So for guys, it's okay, sorry. See that too for new liquids, new gas. liquids, new gas, sorry, kinematic viscosity, gases. For this both of the thing, it means for this both of the thing, it means dynamic viscosity of liquid and simultaneously kinematic viscosity of the liquid. Pressure don't consider, but for dynamic viscosity of the gases, dynamic, we don't consider the pressure, but for kinematic we usually consider the pressure, because here the density is being represented. Here nu equal to what it will come, you just think tau du upon dy. So here density, does it comes? No. So that's why pressure is not related to this. But for this kinematic viscosity of the gases, P equal to m RT. So P equal to density upon RT. So here the pressure and the density is also related. So that's why we do relate for the kinematic viscosity. I think so you got my point. So here there is a been extra thing is been given here. So for this thing I think so no need for this. So we can just go for the next one. So here you just we can go for a question. Liquid with specific gravity, it means specific gravity what is given specific gravity 1.9. So specific gravity is density of the liquid divided by density of the water equal to 1.9. So okay, so first you can look at this. And kinematic viscosity, what is being given? Kinematic viscosity equal to 6 strokes. And the dynamic viscosity, and they are asking the value of dynamic viscosity is what? But I will just put the line. So next thing you can see nu equal to kinematic viscosity divided nu equal to the dynamic viscosity divided by density. So what is been given? 6 strokes into density is 1.9, nu into density equal to nu. So nu equal to what will come? 6 strokes into 1.9 into 1000. It means density of water. So here the strokes must be written as in the what? 1 stroke equal to how much? 1 centimeter square divided by second. So 10 power minus 4 meter square divided by second equal to 6 into 10 power minus 4 meter square per second into how much will come? We just put a 19123 1 point. So meter cube, sorry, kg per meter cube. We just make a cancellation. 6 into 10 power minus 4 into 19 into 10 power 2 into kg per meter second. So we just make a cancellation and you just multiply 19 into 6, 4, 5, 6, 11. So 11.4 kg meter square. I think so you got my point. So option A is the correct thing. So I think so you got my point. So we can just go to the next one. Unlike the viscosity of a liquid, the viscosity of a gas increases with increasing temperature. This is due to correct. So what might be the reason? You just consider for the viscosity of the gases. So increased cohesive force, no. For a liquid only cohesive force will come. So increased momentum, yes, definitely. For increased momentum as only this will come. Decrease, no. And increase in both cohesive force and momentum doesn't come. So for gases, the increased momentum tension will be occurred. So we can go to the next one. The SI unit of kinematic viscosity. What is the SI unit of kinematic viscosity? Here it's been given in the, it means mgs unit. So that's why A option is correct. Okay. I think so you got my point. And see guys, here for dynamic viscosity also been given kg per meter per second. So I think so you got the value. Over here it's been given kinematic viscosity. Okay, let us find this kinematic viscosity. What it will come? Kinematic. So my question number 9, kinematic viscosity equal to for fluids. So nu divided by rho. So kinematic viscosity equal to what will come? Centimeter square divided by second. So centimeter or meter square divided by second, 10 power minus 4. So L power 2 T power minus 1. So what will come? B option. So here I think so the clarity of this thing is not that much clarity, but okay, anyways I'll just give the PDF form so you can have a better understanding. So the next one you can just go, the unit of following property is not meter square per second. What it will come? The dynamic viscosity doesn't have this kind of meter per, but remaining 3 things will have, because kinematic viscosity will have meter square per second, thermal density also. In the HMT, in the heat and mass transfer, I will explain this, and later on I will just explain this in mass diffusivity comes in the chemical engineer. So this also meters per second square will have. So we can just go to the next question. So okay, guys, sometimes the kinematic viscosity is also having the relation with the temperature. So as I told about for liquid, as the temperature increases, the kinematic viscosity decreases. But for gases, as the temperature is being increased, the kinematic viscosity is also increased. Kinematic viscosity. So let me show you the relationship so you can have a better and clear understanding of it. Just one sec, where it is being given. therefore 2. See. See, there are literally two things you have to just understand. See, kinematic viscosity of the gases directly proportional to temperature 3 power 2. So this is just a formula, you have to just mug up it, guys. So you just mug up it so for easy understanding. This is for kinematic viscosity. Kinematic viscosity. For the dynamic viscosity is the rule of temperature. Only for gases. I am not considering about the liquid. I am still having told about the kind of liquid case scenario. I am just telling about only for gases. So for kinematic viscosity directly proportional to temperature 3 power 2. For dynamic viscosity directly proportional to temperature, it means 1 by 2. It means nu equal to directly proportional to power 1 by 2. So I think so, got my point. See, and one other type of thing is for kinematic viscosity, nu divided by density. So you just see, guys, why this nu and why this density is represented. See here, this nu represents the viscous effect. This density represents the inertial effect. Suppose, for example, you just consider this is pen. There's a little bit of distance, so I am dropping the pen in my hand. So this density difference of the pen will apply the force on my hand. Suppose if I took nearly an iron rod, so the iron rod with the same dimension, I am just dropping it, means definitely my hand will get affected. So because of the density of the iron that's been conducted, because of the plastic density, it's so lesser weight. Suppose you just consider about the iron density so much higher, so that's why my hand is little bit pain. So as I told about the viscous effect means what? The internal resistance of the two layers. So kinematic viscosity represents the internal resistance of two layers divided by the inertia effect of the density. So as I am just going, I will just explain each and everything. After finishing one or two questions, we can go for the third one. So I think so you can understand. Wait one sec, it's been problematic. So you can see here the kinematic viscosity of air at 20 degrees Celsius. So guys, for first case scenario, what has been given? Question number 10. What has been given? Temperature T1 equal to 20 degrees Celsius, kinematic viscosity 1.6 into 10 power minus 5, and for kinematic T2 equal to 70 degrees Celsius, kinematic viscosity what? So as I told about, see, it's air is given, air is a gas, it's not a water. So gas. So kinematic viscosity equal to T power 3 by 2. So 1.6 into 10 power minus 5 divided by V2 equal to the relative proportion was equal 20 degrees Celsius plus 273, that we have to write in the Kelvin format, 70 plus 273. So you just add 293 and you just add 343. 20, okay. 1.6 into 10 power minus 5 divided by V2. So you just multiply V2 equal to 343 divided by 293 into 1.6 into 10 power minus 5. You just multiply and put the answer, so the answer will come. So let me multiply and show it to you. So where is the calculator? 343 divided by 293 equal to into 1.6. So okay, how much does it comes? 1.87. So 1.87. Okay guys, anyways the answer is how much it will come? 1.8 into 10 power minus 5, little bit. So here in option it's been not given 1.6 or 3.2, so 1.8 more than 1.8 means literally 2 it's been giving us an equal thing. So I think so all of this question will come similarly in this way of scenario. So okay guys, let me see in the next video. In the next video we are just going to cover a lot of problem to you. Okay guys, then thank you, then have a good day, then bye bye.